Hello everyone. Today I'm going to present a paper, a GPU-friendly Skiplist algorithm. Here is the overview of my presentation. Firstly, I will have a brief recap of the skip list. Secondly, I will introduce you about the previous CPUSkipless algorithm ported to the GPU by Misra and Chaudhry. Let's call it MNC. In this session, I will compare the performance between CPU and GPU. Next, you will have some background about GPU and GPU programming. Then I will bring up the main topic today, GPU-friendly design for a fine-grained log-based skip list. In this session, we will have three operations: contain, insert, delete, and I will give you some examples. In the conclusion section, I will compare the difference performance in GPU between MNC and GFSL. Skiplist is a probabilistically balanced search structures that support expected big O of log n time for online insert, delete, and search operations in order collection. Whether increasing the height will be determined by randomly tossing a coin until we get tail. Let's do some example of insertions. For 23, we had one tail, then we search to the bottom level, and we only have one level. For 65, we had two heads and one tail, and we search for the position for 65. It should be placed after 23, and we have three levels. For 37, we find the position from the top level, we go down, it is more than 65, so we keep stepping down. And then we place 37 after 23. And it has two levels, same for 83. And this is our entire skip list structure after insertion. Now let's perform the contain operation. Let's search 83. So we begin with the top level, and then 83, it is greater than 65. So we go right, and then 80, and then we go down, and then because 83 is greater than 65, we go right, and then we find the 83 here, and we go down, and here is the location of the 83. Let's delete 65. We first search 65 we go from the top level, and then we find 65, and then we keep stepping down. We get 65, and then we remove the entire towel of 65. Because the second level will now become empty, so we also remove the second level. This is the operations of skip list structure. Let's talk about CPUSkipless algorithm ported to the GPU by Misra and Chaudhry. This is a hierarchy of linked list data structure. The behavior of insertion, deletion, and the contain operation is the same as the previous slide. How can we guarantee the linearizable operations? First, make sure that add operation links a new node at level 0 first and moves bottom up. For example, we want to add the key 3 into the skip list data structure. We add it by moving up. Second, a delete operation marks the node to be deleted, starting from its maximum level and moves top down. For example, we want to delete the key 7 from the data structure, and we delete it and we remove the tower by moving down. As you can see, it might require multiple atomic class operations in insertion and deletion. Let's compare the performance between CPU and GPU. The x-axis represents the key range, like from 0 to 100, from 0 to 1000. The y-axis represents the GPU speed up over CPU. So it's a ratio, GPU over CPU. And each bar represents the number of operations, like 10K operations, from 10K operations to 100K operations. Skiplist is evaluated on two different types of operation mixes: 20% add, 20% delete, 60% search. 40% add, 40% delete, 20% search, we can see that significant speed up on the GPU compared to the CPU implementation for small and medium key ranges. With the add percent increases, the speed up also increases, as we can compare these two graphs. Also, as the key range increases, the speed up drops sharply. It is due to the overhead of atomic cast operations and complicated control flow of the implementation. More add and delete operations have to modify the data structure through atomic cast operations. But as we can see here, in the 40-40-20 mix, it also has a speed up of nearly 4 on large key ranges with 100,000 operations. As we saw with the same classic Skiplist algorithm, GPU has better performance than CPU. Why does GPU have better performance than CPU? First, GPU provide hundreds of computing cores at high energy efficiency. Second, GPUs are very effective for regular coalesced access data parallel computations on large data sets. Why do we need GPU-friendly algorithm design then? First, irregular coalesced access to memory and control flow divergence in applications can severely impair performance, like dynamic updates and accesses. Due to that, many algorithms developed for CPU and ported to GPU are required further GPU optimization. These three keywords, I will explain it in the next two slides. I'll give you some background of GPU programming model CUDA. Threads are subdivided into blocks. Blocks are distributed among streaming multiprocessors in GPU. We also call it SM. Streaming multiprocessors are the computational engines of GPU. Streaming multiprocessors further logically subdivide blocks into warps, which are the basic unit managed and scheduled by the SM. A warp usually contains 32 threads in NVIDIA GPUs. Threads in a warp share a program counter and proceed through kernel code in lockstep. Warps on a streaming multiprocessor are interleaved in order to high latency. When a block terminates, the streaming multiprocessor receives and executes a new block until all blocks have been handled. Let's talk about GPU uncoalesced access and coalesced access. In terms of the speed of moving frequently accessed data to fast memory, we have the relationship here, and we are focusing on the global memory access. For coalesced access, we have warp of 3 threads. The memory location we want to access are contiguous. In this example, all the memory locations we want to access are in one chunk, so we have one memory transaction. For uncoalesced access, we also have a warp of 3 threads. And the memory we want to access are strided. So we can also say it is a strided memory access. In this example, we have 3 memory transactions because we have 1, 2, 3 chunks we need to access. GPU most efficient when threads read or write contiguous memory locations. In terms of branch divergence in a warp, once a block is assigned to a streaming multiprocessor, it is split into several warps. All threads within the warp must execute the same instruction at the same time. Now we have a problem. If and else branches cannot be executed concurrently, here is an example. We have a warp of 6 threads. And we go to the branch, and 3 of the threads go to the if statement, and 3 of the other threads goes to the else statement. In this case, we need to double the time inside the branch. It will result in performance loss. This is not good, but we have nothing to do about it. We need to ensure if statement cuts on warp boundaries. As we can see, the previous classic CPU-Skipless algorithm ported to GPU by MNC provides little locality of data, causing uncoalesced memory access on the GPU. Since it is a linked list data structure, we cannot control the memory location which store keys. It also presents a high probability for divergence of threads with the same warp. Each thread that operates on a different key will have a unique traversal order, potentially causing many branches between the threads. Thread level synchronization on the GPU is very costly, especially when necessary between any pair of threads in the system. The unit between GPU and CPU are different. CPU uses threads as units, while GPU uses warp as a unit. As you all have the background now, let's go back to our main topic, GFSL. Instead of being a linked list data structure, GFSL consists of array-based skip list nodes. It allows threads in a warp to cooperate in the execution of the skip list operations. GFSL consists of several levels of truncated linked list, each containing a subset of the keys in the level below. We will explain the concept of chunk in the next slide. In the upper levels, the value field of each entry in the data array points to a chunk in the level below. And in the bottom level, this field will hold the data element associated with the corresponding key. A key value pair in the level I generally points to a chunk containing the same key in level I plus 1, though it may temporarily point to a chunk containing smaller values during inserts and deletes. Threads are divided into groups called teams. The size of team can be defined by the user, normally a warp. The threads in teams can be divided to data threads and next threads. Data threads is to check whether its value is a candidate for the down step. Next thread is defined by checking whether a lateral step should be taken when max value in current chunk is smaller than key. And CUDA provides two helpful functions for threads to communicate. Ballot gives each thread a bitmap mirroring the result of its computation. SHFL returns the value if a variable held by a thread at a specific channel within a warp. Now let's look at how GFSL tackled the uncoalesced asset problem. It is done by chunk. Chunks is defined by packing consecutive key value pair residing in the same value. Chunks contain a data array, max field, next pointer, and a log field. With the chunks design, we can have the coalesced assets in the skip list as data in chunks can be read efficiently in the field with possible memory transactions. The number of entries in the chunk equals number of threads in a team. So here we have n-1 data threads. And then the entire chunk is read in a single kernel instruction. In the contain operation of GFSL, structural traversal is very similar to the traversal over a regular skip list. A contains operation that must wait for a log to be released may result in high contention, especially in the massively multi-threaded environment of the GPU. We would like contains to be as fast as possible, so we design contain as a log-free operation. Here we have an example. Look at this chunk. If the key we inserted is greater than the maximum node 15, then we do a lateral traversal. If the key is less than the smallest node 10, then we do a backtrack to the previous node. If the key is between 10 and 15, then we do a step-down traversal. And now we define zombies as a deleted chunk marked by deletion threat. The contain operation calls two main functions, search down and search lateral. We'll explain these two functions in the later slides. Now we do example of search 17. The team begins by reading chunk A, the first chunk in the top level. Each data thread checks whether its value is a candidate for the down step less than or equal to 17. And we see 68 is greater than 17. The next thread checks whether the maximum value in the chunk is smaller than 17, meaning a lateral step should be taken. And we can see in the chunk A, the maximum value is infinity. So we do not need to do the lateral step. We do a down step. With ballot, the thread can see that thread 0 is the highest thread that returns true and retrieve the pointer from 0, thread 0. The entire team then steps down to chunk B and repeats the computation, finally stepping down into chunk E. In chunk E, each data thread checks whether its key is equal to 17. Note that it's just one single kernel instruction, while the next thread continues to check whether a lateral step should be taken. The ballot operation shows that T2 sees key 17, and the team concludes the operation with the true indication. Now, let's talk about the functions search down and search lateral. Search down can be used to handle traversal of the upper levels. It can retrieve the height and the pointer to the first chunk. Each thread reads a separate space in the head array to see whether the level corresponding to its TID thread ID in use. The team then discovered the highest non-empty level and retrieved its pointer. In each iteration, the team reads chunk to decide lateral step or step down or backtrack. For search lateral, it is used to search along the bottom level. Data threads evaluate whether the key they read is equal to k. The team calls getTID with key to determine the next step and continues to take lateral step as long as the next thread ID is returned or the current chunk is a zombie. Return value would be none, indicating that k was not found, or thread ID of some data thread indicating that k was seen by the thread. And we have a special case in the log-free contain operation. So if a team 1 search for 17, we have chunk A to chunk C, and then it sleep. Note that T2 then deletes 59 and 68. Team 1 wakes and see all values in chunk C is greater than 17. We want to do a backtrack, but there's no information to backtrack because it cannot backtrack to the previous chunk. So we need to restart team 1 search. In terms of GFSL insert operation, we search for the key first and get the chunk's path. The enclosing chunk in the bottom level is locked once it is reached and found not to contain k. It remains locked until the insert operation is completed. And then we insert the key into the enclosing chunk. Let's do an example. We want to insert 18 into Skiplist. We start with the chunk A, which is the top level chunk. As 18 is greater than negative infinity and smaller than 68, we do a step down traversal and go to chunk B. 18 is in between 13 and 30. And we have a step down traversal, we go to chunk E. Chunk E is our enclosing chunk, but we did not find 18 in this chunk. So we lock chunk E. And we want to insert 18 into chunk E. Then we have two conditions. If chunk E is full, this causes chunk E to be split. The team will then lock chunk B and perform an insertion, then unlock chunk B. If chunk B is full, the team will perform a similar insertion into chunk A. Otherwise, the team unlocks chunk E and returns true. Also note that when a zombie is discovered after a lateral step, the team attempts to redirect the previous chunk's pointer to remove the zombie from lateral traversals. The redirection is performed lazily by calling try lock on the previous chunk. If the lock fails, the team continues without updating. And if an insertion occurs when there is no free space in the data array, a split operation is performed. And then I will show you how the split operation is performed by giving some examples. Without split, in the example of without split, we insert 10. All keys higher than 10 are moved one tree to the right. With split, we insert 22. Keys 20 and 25 are moved to the new chunk. The original chunk's next pointer and the down pointer associated with the key 20 in level I plus 1 are redirected to the new chunk. And here are some details of the insertion. Note that we don't use local array to store paths as it is costly in CUDA. We store the path as an artificial array consisting of a single variable per thread. The thread with thread ID I holds the chunk in level I in path. The array is accessed using SHFL operations. So here is the example. We have A, B, E path, but we don't store as an array in CUDA. So we have three threads. This is thread 0, thread 1, and thread 2. And thread 0 contains chunk A. Thread 1 contains the pointer to chunk B. And the thread 2 contains the chunk pointer to chunk E. In GFSL delete operation, we also search for the key and get a traversal path similar to the insert operation. If key K exists in the structure, we lock the bottom level chunk, then encloses K. The team then searches all occupied levels from the top down, removing K in every level in which it is found. The chunk in the bottom level remains locked until the delete operation completes. Let's do an example. We want to delete 13. And we search for 13 first, and we find 13 in the skip list. We get a path A, B, E. And then we lock the bottom level chunk that encloses K, which is 13. And then we see there is no 13 in chunk A. And then we go to chunk B. 13 is in chunk B, and we remove it. And then we go to chunk E, and we find 13 in chunk E. And then we remove it. And then we unlock chunk E. Note that removing the key can cause several cases. First, without merge. For example, we delete 10 in the chunk, and then we just need to move every node after 10 to the previous position. Second condition, if K is the last element in the chunk. the next thread must update the max field. This must occur before the deletion of the key so that concurrent searches do not see a max value that does not exist in the trunk. So in this case, let's say we want to delete 4, and then we need to update the maximum value field. And the highest thread to see a non-empty value in its entry must make it empty. So we have a thread which is comparing the node 4. We need to make it empty in this case. With merge, if removing k will cause the number of non-empty entries in the data array to cross a predetermined threshold. So for example, we have a part of Skiplist like this. And then we delete 3. So in this case, we need to merge these two chunks. And then we have a new chunk. And we need to make the previous chunk in the upper level to point to this. Also, we have the last scenario. K is in the last chunk in the level. We just need to remove all the entries in the trunk. Here we have some reflects on GFSL. We notice that all operations in GFSL are designed to be performed in the unit of the team, with only a few divergent thread ID specific operations scattered throughput. This reduces the divergence. And every global memory accessed by a team is accessing contingent memory locations. And that is the coalesce access. Finally, we reach the last section of GFSL. We would like to compare the performance between GFSL and MNC classic Skiplist algorithm in GPU environment. The x-axis represents the key ranges. The y-axis represents the speedup of GFSL over MNC. We can see the speedup of GFSL over MNC. As the key range increases, the speedup also increases. The main advantage of GFSL is the usage of the coalesce reads, which optimizes accesses to the global memory. In the smaller key range, let's say 10K, the entire structure fits into the L2 cache in both implementations, which significantly reduces the benefits of coalesce reads as L2 access is much faster than the global memory access. However, in larger key ranges, MNC requires frequently uncoalesced accesses to the global memory that causes a sharp decrease in performance. GFSL does not suffer from this. And we also have the single uptime test. 100% contains, 100% inserts, and 100% deletes. All graphs show higher performance for GFSL over MNC in all ranges. And we also have further future work. First, we can build GPU-friendly algorithm on other linked list-like data structures, such as linear probing, hash map, and priority queue. Secondly, warp is not defined in the OpenCL standard. OpenCL cannot expose every feature that CUDA can expose for warps. In terms of OpenCL or other parallel programming platform, we might need to create another GPU-friendly algorithm for the linked list-like data structures. Here are the references. And thank you for listening.